Matthew Soulanille. I'm a software engineer on the TensorFlowJS team at Google. I'm here to talk to you about TensorFlowJS. So, why should you use TensorFlowJS? Well, it has no installation requirements. It runs in the browser, which everyone has. There's no packages or deliverables that need to be installed. It's just JavaScript over the web, like everyone's used to. It's interactive. It's very easy to access sensors like the webcam and microphone. It has very good privacy qualities. All data stays on the client. There's nothing that gets sent back to the server, unless you specifically want to do that. But you don't have to. Latency is very good as well, since everything is running on the client. There's no ping time to go back to the server and then back to the client with the inference results. And it's JavaScript native. So everyone who's familiar with web development and JavaScript will find it very easy to get started with TFJS. And so what's TensorFlowJS for? Well, it allows you to create pretty much anything you can dream of in the machine learning space. So let's take a look at what some people have been creating. These are just like examples from users who have been using TFJS in their own applications. So here, InSpace used real-time toxicity filters in their web conferencing app. And you can see when a user enters something bad, it's flagged before it's even sent to the server for processing. And it alerts the users that they might want to reconsider what they're about to send. Next, we have Include Health, who's been using our pose estimation models to enable physiotherapy at scale. Well, many folks were stuck at home during COVID and unable to travel remotely. This technology allowed for remote diagnosis from the comfort of their home using off-the-shelf technology, just a standard webcam that everyone has access to. Well, almost everyone has access to. Or how about enhancing the capabilities of a typical fashion website? Here, we have a body segmentation model with some custom logic to estimate body measurements and allow the website to automatically select the correct size t-shirt at checkout. And this was made in under 2 days using our pre-made body segmentation model. You could also bring a character to life by combining multiple models. In this demo, there's pose estimation for getting the arm poses and face mesh for the facial expressions. Now, traditionally, creating animation is a hard problem, but this pose animation tool by partner innovation here at Google allows you to draw any SVG character you'd like and give animations to them in with motion capture in real time. And you can take this even further with 3D characters, like this great demo by Richard Yee from our community. And this allows you to use your favorite character as your virtual avatar for meetings or live streams, enabling real-time motion capture to drive virtual artists in the browser. And this, of course, just uses a regular webcam, all running in JavaScript. Looking into other creative applications, you can turn your voice into a musical instrument using Google's Magenta Tone Transfer model that runs in the browser as well through TFJS. You can sing any song or tune you wish and hear it being played by an instrument of your choice. Or what if you could make the world more accessible? Here at the partner innovation team at Google, here the partner innovation team at Google used TensorFlowJS to understand sign language gestures. This project is built using a combination of machine learning model outputs for face, hands, and body to account for the fact that sign language is communicated not only by the signer's hands, but also with their facial expressions and overall body position and posture. Currently, the demo has been trained on JSL and HKSL phrases, but it could scale to any sign language dialect. Even better, this library can be used for any sort of gesture recognition, even beyond sign language, and it is generalizable to any human-computer interaction use case, which opens up possibilities for web-based creative experiences, fitness, health, and even human-computer interaction research. And everything you just saw was powered using pre-made models. You didn't have to do any machine learning modeling or training to get these effects, just using the standard models that we have available. So pre-trained models let's take a look at some of the ones we have available. These are easy to use JavaScript classes for common use cases and are great for people new to machine learning or even people that are new to JavaScript and are looking to understand how to work with the web stack. Since launch, we've released many pre-trained models, and we're currently expanding our selection, which we'll hear about more shortly. We have models across many categories, such as vision, body, text, sound, and these just take a few lines of code to use. If you want to check these out, you can go to TensorFlow.org/js/models to see all of them. And yeah, even better, you don't need a machine learning background to use any of these. Just a working knowledge of JavaScript is useful. So let's take a look at some of these in action. First up, we have object recognition. Here, we're able to run the popular Cocoa SSD model live in the browser to provide bounding boxes for 90 common objects that the model has been trained on. This allows us to not only understand where in the image the object is located, but also how many instances of the object are in the image, which is more powerful than just image recognition alone. Next, we also host a 3D pose estimation model in collaboration with MediaPipe, which is another research team at Google. And this can estimate 33 key points on the human body in real time. This model has 3 forms: a light form, a heavy form, and a light, full, and heavy version. And these allow you to select between a trade-off of accuracy and speed. The light model, for example, can run at 150 frames per second on a modern desktop computer with a discrete graphics card. A bit slower on laptops, but still very performant. Continuing our MediaPipe collaboration, we've also released a body segmentation model. And here you can now retrieve the segmentation mask as well, in addition to the key points. And this shows which pixels belong to the human body versus those that do not. You can see in the red and blue animation up there. Yeah, and like I said, this expands on the pose estimation model that you saw before. So you can get both of these results with minimal overhead. Yeah, and this model is now part of our unified pose API, linked on the slide, that shortened Google link right there. So if you need both pose and body segmentation returned at the same time, go check it out. Now, related to this, there's also a version of this model that's optimized for selfie segmentation. And this allows you to create effects like the one that I'm sure all of you have been using throughout the Zoom call, where you can like replace your background with a different background or make add a bokeh effect, stuff like that. And this model is actually a modified version of the one we use here internally at Google in Google Meet for conferencing. And this version of the model is better suited to close-ups, as you can see here, where the user is less than like 2 meters from the camera. And it can run pretty quickly as well, about 200 FPS on a modern computer with a graphics card. Yeah, and you can check it out at the link shown. More stuff related to human bodies. Moving on to the face this time, we have updated our face landmark detection API that builds on the existing face mesh model that you may have tried before. And this new API has even higher accuracy for detail for face landmarks and movements. And it's also based on the latest MediaPipe model. And you can see in this demo, it can run at over 130 FPS on modern computers. Yeah, and you can try it out at the link below. This frame rate, though, is probably from like a computer with a rather beefy GPU, so you might see slower frame rate on your laptop. But yeah, there's also a very lightweight option that just returns bounding boxes and 6 key points for the face if you have a less powerful device like a smartphone or something like that. And for a more in-depth look at what can be done with faces, we now have the selfie depth estimation model. And this is capable of estimating the distance from each pixel in the camera as capable of estimating the distance of each pixel on the scene from the camera that's taking the picture. And you can see this, maybe I can, oops, sorry. Laser pointer mode. yeah, and you can see this. You can see this depth map right here. First, the model will segment using one of the image segmentation models I discussed before, and then it will apply the depth map to get the depth map of just the person space. And you can do some pretty cool things with this, such as 3D photos. You can see it might not be showing up that great on Zoom, but it sort of like wobbles around the person's face and gives you kind of an idea of what a 3D version of them would look like. And you can also do things like imagery lighting. Here, the user is able to use 3.js, which is a 3D graphics library, along with some custom shaders to cast light rays around the person in the scene, since we have the depth information from that depth model. Next, let's turn our focus to hands. Some updates to our hands model now allow tracking of multiple hands at the same time in 3D or 2D with higher precision than before. On a modern desktop computer, you can get about 120 FPS with this kind of model. And yeah, this, like I mentioned before, with the sign language interpretation, these kinds of models can be very useful, along with the pose estimation for combining and forming something that can really provide a cool thing that you might not necessarily be able to get with them on their own. So that brings us to the question that I'm sure you're all, well, asking. What do these APIs actually look like, and like how are they to use? So as an example, let's kind of shift away from video and talk about text processing. And I promise the video APIs are also similarly easy to use. It's just video is a bit difficult in general. So there's kind of a difficulty floor there. They all have to be at least as hard as video is difficult. But yeah, so for this example, we'll be using our BERT Q&A model, which you can give it a large body of text and then a query, like when was Nikola Tesla born, for example, and then you give it his Wikipedia article, and then it will find like parts of that text that it thinks are relevant to your question. So in this example, we're going to try to build a Chrome extension where you can just type in a question and it will find the relevant part of the article that corresponds to that question. And this just takes a few lines of code in the core part of it. There's more setup required for the actual extension, but the actually using the BERT model is relatively simple. In fact, the code fits on a single slide. So let's walk through it. First, we import the TensorFlow.js library and the pre-made model that we want to use, which is this BERT Q&A model, question and answer model. Then we just set up some text that we're going to query and the question that we're going to ask. Normally, you would be scraping this from the website, but for this example, we're just going to make up some text. And afterwards, we'll load the question and answer model itself. This takes some time to load since it's doing a network request, so it returns a promise, hence the .then. You give it a callback, which will be called with the model, and then you can do model.findAnswers. We pass this function the question we want to answer, and then the search text we want to find the answer in. This is also asynchronous, so it returns a promise. So we do .then answers, and this will be called with the result of the model. This will take a few milliseconds, and in this case, it would predict cats, because what is important on YouTube? Well, of course, cats. And that's pretty much all there is to it on the model usage side. Of course, there's a bit more involvement with actually creating a browser extension, but the API here is relatively simple when it comes to finding an answer to a question of arbitrary text. So that really covers, and our other models are similarly easy to use. For some of the vision ones or the image-based ones, you can usually give them a document element or like an image tag or a video tag, and they can run on that and provide you with like classifications or key points or things like that. So what if there isn't a pre-made model that works for you? Well, we also support transfer learning, where you take an existing model and then retrain the last layer of it to do something slightly different. And our go-to example for this is Teachable Machine. And if you haven't seen this website, definitely take a look after the presentation. You can take a few different images from like for one class, like up here. You can see, maybe you can see, but in this example, he has his hand up. And in class number 2, it's just his face. And yeah, you can just train the model in the browser. This is based on, I think, MobileNet v3, and it just retrains the last layer of it. And you can just build your own model just in the browser. And this is great for prototyping ideas and getting a feel for how to use TensorFlow.js. This can export to TF-Lite and TFJS. And I think it might also be able to export to Keras, although I'm not totally sure on that. Oh, I think some versions, some of the models it has can also export to TF Micro if you're interested in running on microprocessors. Still though, outside, some cases can't be covered by all that. So outside of our pre-made models, you can, of course, write your own models from a completely blank canvas. So we have this API website. It's has some stuff that you can see our full API here, but I'll give a quick overview of how this works. There's two sort of different APIs that we have. There's a high-level layers API, which is very similar to Keras, if you've used that before. And there's also a low-level ops API, which is more like a linear algebra library. And these are sort of built on top of each other. So at the top, we have our pre-made models. Some of these are built on top of layers. Some of these are built directly on top of the core ops, or we also have a graph API for if you convert a normal model, or a normal TensorFlow model, then it will kind of skip the layers and just go directly to core ops. Then there's these ops will run on the client, and this is compatible with many different environments, like the browser, React Native, things like that. And each one of these environments can execute on a number of different backends. Now, by backend here, I don't mean server-side. Backend in this context refers to the actual hardware that it's running on. And I'll get into some more details on that in a bit. Oh, actually, right now. Sorry. So what backends do we have available? We've got the CPU backend, and this is always available, and it's the slowest form of execution. This just runs each machine learning op as JavaScript, so it's pretty much guaranteed to be available. If you're able to run TensorFlow.js, you're able to run the CPU backend. Now, you also have WebAssembly, and this is CPU execution, but faster. It has support for single instruction, multiple data, and in some cases, you can also get multi-threading working. Smaller models can run extremely fast on the CPU, so this can be very good for those cases. Sometimes it can take a long time to copy textures to and from the GPU. Yeah, and in some cases, this can even match GPU performance. And then, of course, you also have, kind of like I mentioned, the GPU, you've got the WebGL backend. And this leverages the graphics card and supports 96.7% of devices. There's a few that don't work yet, but we're trying to get there. We're trying to close that gap. And yeah, that means you can run more than just NVIDIA graphics cards. Anything that supports WebGL, which is, I think, pretty much any modern smartphone, computer, anything like that, should support our TFJS WebGL backend. Yeah, and this includes like AMD cards and, of course, Intel integrated cards, although they have some discrete ones these days, and also Apple. And yeah, looking towards the future, there's some really exciting new APIs and web standards. So there's WebNN, which is kind of more focused on bringing native APIs for machine learning, bringing access to them to the browser. So you could maybe send a graph of machine learning operations to be executed to the WebNN API and the input, and then it could send you the result of executing that graph on like native C execution instead of in WebAssembly or the CPU. Then there's also WebGPU, which is kind of a successor to WebGL in a sense. It provides a much deeper access to the user's graphics card, and it's much better for the compute kinds of applications that are involved with machine learning. And this one is actually, I think, almost ready for just general availability. I don't know exactly when, but I think the Chrome team is planning on flipping the bit to enable it in Chrome sometime this year. I'm not completely sure. That could of course change, but yeah, once that happens, we've been seeing some really good performance on this backend. And I also want to give a shout out to Intel for the really good work they've been doing here. They've contributed so many ops to this backend. We probably wouldn't be nearly as close to full coverage with it without their support. So that's the website. Let's take a look at the server side, because you can also use TFJS in Node. Note here that our Node.js environment supports the same TensorFlow CPU and GPU bindings as Python. These things right here are actually just the native C bindings to TensorFlow. So all of the op implementations and everything here can get the same or similar performance as what you'd get in Python, because it's using the same backend essentially. Which means you can get CUDA, AVX acceleration, and yeah, everything you'd expect with Python in terms of running inference in models. There's also some advantages you get from using Node.js instead of Python as a server, which is that Node tends to be a bit faster in some cases because it has a just-in-time compiler. If you're doing a lot of data pre-processing, you might find some performance benefits from Node. Let's see. Sorry. I think I may have just set the entirety of this slide on the previous one. So some example of that we've seen. So what's our performance like here? As you can see here, executing this MobileNet v2 model, which is an image recognition model on both Python and Node with CUDA GPU acceleration, leads to about a millisecond of difference. This is very similar execution time. However, if you do a lot of pre-processing, like I said, this might be an advantage for Node. For example, the company Hugging Face, who are well known for their natural language models, converted their Distilbert model implementation to Node.js. And for them, it resulted in a 2x performance boost over the Python equivalent. So yeah, if performance is top of mind, you may want to give Node a chance, especially if your goal is to expose a server-side web API for inference, which Node is well suited for, very easy to develop and deploy. In summary, here are some of the benefits of Node on the server side. First, you can use the TensorFlow saved model format without converting it to TensorFlow.js. Normally in TensorFlow.js, if you want to run a normal TensorFlow model, you'll have to run it through the TFJS converter first. And this lets you run, or not having to do that, lets you run, and also not having to ship it to the user's device, lets you run much larger models. Next, you can code in just one language. If you were running TF in Python and trying to serve stuff in Node, this removes that requirement. You can do your whole server in Node.js. Yeah, finally, performance. Just the JIT compiler is very good at getting high performance from pre-processing and post-processing code. Of course, there's ways to excuse me. Of course, there's ways to do that in Python too, if you just keep everything in NumPy and use the C bindings. But it can be easy to do this in Node as well. And yeah, and finally, let's talk a bit more about the client side and what you can achieve there. Just to kind of reiterate everything I've been talking about so far. The first benefit here is really privacy. There's no information stored on the server. Everything is done on the client machine. This is particularly important for industries where it may be a requirement to not transfer data to third parties. Additionally, there's growing concerns about privacy these days. And here, you get privacy for free with TFJS. Like I mentioned at the beginning, lower latency. JS has direct access to device sensors such as camera, microphone. You don't have to do a round trip to the server. Latency could be as close to 100 milliseconds on mobile connection over 3G or 4G. So that can really hinder model performance or just quality of the experience. But with TFJS, there's none of this. I mean, of course there's some other things you have to worry about, like battery life and things like that, but you don't have to worry about latency. Yeah, there's also no data being sent to the server, so you don't have to pay extra networking costs. You don't have to buy servers with GPUs. And yeah, interactivity. Web is really designed for the display of content. And from day one, it supported graphical content that has evolved to handle richer and richer formats like WebGL, things like that. And as such, it has very mature libraries for graphics and data visualization, like 3JS and D3.js. And this allows you to code your ideas quickly, which is very important for developing new models and just getting feedback on them. And yeah, finally, reach and scale. Anyone who can click on the link and load the web page should be able to see how your model works. 0 install required. And yeah, you can get more eyes on the cool projects and models you're working on. So finally, I'd like to summarize some resources that you can use to go further. For more hands-on, step-by-step instructions, check out our code labs at codelabs.developers.google.com. And you can simply search TensorFlow.js or TensorFlow.js on this site to find a whole bunch of useful step-by-step guides. If there's one slide to take a screenshot of, this is probably the one. Here you can find our website for more details on the library or check out some of our pre-trained models. You can also view our open source code on GitHub and even make a contribution if you want. I know some of you already have. And yeah, you can check out the official TensorFlow forum as well to ask more technical questions. And remember to tag your post as TFJS so we can find it. We'll also have some code examples that you can fork and over at glitch.com and codepen.io. And these can provide some boilerplate code to get you started. And of course, for inspiration, check out our short 10-minute interviews on YouTube made via our made-with-tfjs series. Yeah, for further reading, I recommend checking out these 2 books on the right. The first is by O'Reilly, and it's a good, easy to follow introduction to machine learning and TensorFlow.js. The second is by Manning and was written by folk on the TensorFlow team here at Google. And it goes a little deeper for those interested. Let's see. And yeah, come join our growing community. There are too many examples to show here. And there's more coming out every single week. So you can check out the made-with-tfjs hashtag on social media like Twitter and LinkedIn to see what people are making around the world. And yeah, if you make something, be sure to tag it too. And you might be featured in one of the events that Jason, our developer relations engineer, hosts. So the only thing left to say now is, what will you make? My final example here is by a member of our community from Tokyo, Japan. He's a dancer by day, but he has managed to use TensorFlow.js to create an amazing hip-hop video with some pretty cool visual effects using body segmentation. Now, the reason I end with this is that machine learning really now is for everyone, no matter what your background is. And I hope TensorFlow.js can be can enable more people than ever before to find it and start their journey with machine learning. Feel free to connect with me, stay in touch. I'm Matthew_Soulanille on the TensorFlow forum, or you can also check out the Discord server. I think I'm Matt S there or something like that. And yeah, you can also reach out to Jason Mays. He's our developer relations engineer, and he's done so many cool demos and some really cool YouTube videos and talks on TFJS. You can just search made-with-tfjs on YouTube, and you'll find a lot of the content he's made. So yeah, again, thank you for listening. And if you're wanting to further your knowledge, check out these links on the right. And yeah, that's all from me. So I'll open it up to questions now. Thank you.
Thank you. Wow, thank you very much, Matthew. That was awesome. Really appreciate everything you just shared there. What I'd like to do, as Matthew just said, is open it up to questions. If you don't mind raising your hand, we're going to do that in some kind of order, and we'll just kick it off with Forrest. Please kick us off.
Hi, Matthew. Thank you. Very cool talk. It looks super fun to play with. I have so many questions, super interesting to discuss, but I guess one of the questions that I'd like to clear up, I've been thinking a lot lately about the comparison between Python and JavaScript. And you mentioned when you were comparing TensorFlow speeds in JavaScript and Python, that it was JavaScript's just-in-time compiling that made the difference here. And what I was curious about was, I'm pretty sure that Python is also an interpreted language that does just-in-time compiling. So I guess seeing the difference there, is it like the V8 engine and how it has those two steps, like the early interpreter and the following interpreter, that makes the difference, or something else? Thank you.
Yeah, really great question. My experience with compilers is definitely not as much as other people at Google, but I can say that the V8 team is, I guess, yeah, extremely well funded, in the sense like Google Chrome is one of their biggest products, and they just put a ton of engineering effort into optimizing it as much as possible. On the Python side, I also want to mention, like, you can also use, I think there's some other Python interpreters that do a bit better than the standard interpreter. I think Cython, one that's like based on C, or I think it has some more C bindings that will automatically activate or something. I don't know exactly how it works, but there are definitely some really impressive Python interpreters that get great performance. Again, though, if you're doing pre-processing and you just want to like really quickly write it out in an easy to do way, Node can be very good at that. If you want to do it like, I guess I don't really want to say properly, but if you use like NumPy and C bindings and stuff like that just throughout your program, then yes, definitely Python can get same or better performance just because it's all running in those bindings. So I don't want to be misleading at all there. So I guess with that point, I really want to say, like, yeah, if you're just doing all the pre-processing in the language itself, then yeah, Node can in some cases be faster. I hope that answers the question.
Yes, thank you.
Awesome. Adam, take it away.
Yeah. So a lot of the examples you showed were of taking like pre-trained models and running inference in the browser. As edge devices get better compute and we get like better APIs to their GPUs like WebNN, do you anticipate that a lot more model training will be happening on the browser? Because you did mention like all of the benefits you get from actually training training models there and keeping your data there?
Great question. Yeah, that's definitely an open area of research these days, I think. So there's a lot of difficult things with training models on the browser in a way that like scales to the point where you can get something that's like a useful model. Well, okay, I don't want to say that other models are not useful, but I guess what I mean is if you just train something on Teachable Machine and then download it, that's essentially just your model, and no one else is really able to use it. Now, Google has been working on, I don't know if you've all heard of federated learning. I think it was in the news a while ago as like the evil new thing that Google was going to use to track you. But it also has it has application. Its whole thing is about training a model a few steps forward in one person's device, then saving that result in a way that's privacy preserving, and then sending that to a new person's device to train it further. And I think this is mostly me speaking from my own opinion. It's not really what Google's doing, because I don't really have any insight into these areas at Google, to be perfectly honest. The federated learning side of things, I mean. This kind of thing, I think, like you said, I think this approach might give you the ability to train much larger scale models on users' devices in a privacy preserving way that lets us, get some really cool models that we normally wouldn't really be able to get due to privacy concerns and not wanting to use users' data. I hope that answers your question.
Yeah, thank you.
Awesome. Jared, go ahead.
Thanks. Hey, Matthew, great presentation. I really appreciate it. To get kind of an insight into what your role looks like, I would love to know if there's a project or task that you recently completed or one that you're about to complete that you're like especially excited about.
Oh, yeah. So at Google I/O, I think last year, I created this demo or this code lab to show you how to run TF Lite in Node, and it uses like Node bindings. That was actually kind of based off of our existing TF Lite on the web bindings that run in WebAssembly. So that work has actually kind of continued in a sense. And what I'm one of the key features about being the Node side of things was the ability to use TF Lite delegates. Now, a TF Lite delegate is essentially TF Lite's version of hardware acceleration, or in some cases, software acceleration, where you can like say, I have this TF Lite model, but I want to use the graphics card to run this part of it. And if you have a delegate that can do that, you can kind of cut the model graph up into pieces and send the pieces that are supported by the delegate to be run accelerated on the GPU. Now, that all works in Node because TF Lite is written in C++ and C, and the Node bindings just bind to those. But that doesn't work on the browser yet. So the thing I'm really excited about is I've been trying to get this working on the browser as well, and get delegates working there. I don't know if it's actually going to work. So if you don't ever see this, that's why. But that's one of the things I'm most excited about, and one of the things I'd really like to get working in the future. This would let us do things like run TF Lite models on the web with GPU acceleration or WebNN acceleration, because WebNN is really good at like running a graph of a model, and TF Lite delegates really want to like give you a graph to run. So that's kind of a perfect fit there. And yeah, also with this project, I want to mention Intel has been doing a lot of the work on the actual delegate side of things. So definitely thanks to them for helping us push this project forward. Yeah, that's pretty much what I've been working on.
Awesome.
That's really neat. Thank you.
Matthew, I would love to actually just ask you kind of a basic question a little bit on going back to the work that Adam and David from Codesmith have done with you on the interoperability between the Python version of TensorFlow and the JS version. What does that interoperability mean in real world sense? How does improving that interoperability kind of show itself?
Yeah, great question. So that one of our really big goals is to just be as easy to make the library as easy to use as possible. And the fewer steps people have to do in terms of like pre-processing before their model and post-processing after it, the better. And these new ops that have been implemented are really for those kinds of pre-processing and post-processing steps. And if you can take a model in Python that uses keras pre-processing and just convert it to TensorFlow without having to manually rewrite those ops in like JavaScript or something like that, and just call the like native TensorFlowJS ops that you guys have written, that makes that process a lot easier. Yeah, so thanks so much for the contributions you've made. It's always great to see contributions from people who are interested in the project.
Yeah, that's awesome. Actually, one of those contributors, Adam, you have a question.
Yeah, I actually had a question just about TensorFlow Lite. Just what about TensorFlow Lite makes it smaller than TFJS? Is it just like kept in that graph representation, or how? Yeah, what makes it smaller than just a normal TFJS model?
So I'm not totally sure that that's the case. It might be. I'm just actually not sure. There's TensorFlow models. Those are usually like saved in a way that you can retrain them or reload their weights and continue training. TensorFlow Lite models are saved usually for deployment only. There's a limited amount of training you can do in TF Lite with like transfer learning on the last layer of the model, but usually you're just saving a model for deployment. That is usually the cause of less weights between TensorFlow and TensorFlow Lite, as I understand it. I might be mistaken there as well. I'm not actually all that experienced with training models. I mostly work on the JavaScript side of things, so if I'm mistaken there, sorry. In terms of TensorFlow Lite versus TensorFlowJS, if you're seeing model size differences there, it may be due to how TensorFlow Lite stores their model. They, I think, store it as a flat buffer, and they also support loss of quantization. So you can quantize your model down to like uint8, and that can save a ton of space versus like float32 or something like that. Yeah, that, and then, yeah, TF Lite models are also kind of just a single flat buffer, and that does make it a little bit difficult to load larger ones on the web. If you like kind of fail to load the entire model during the page load, you won't get the caching that you might get with TFJS if you've like loaded some of the 4 megabyte chunks and then the page fails to load, then you can reload it, and the ones you've loaded so far should still be cached. But yeah, those are just some details that I know on the model format. Yeah.
Cool. Thanks.
Awesome. Thank you again for being with us tonight. This was fantastic having you here and sharing everything you did. We all appreciate that tremendously. Thank you to Codesmith, obviously, for hosting, and for everyone putting this together. Laura, obviously, thank you so much. But honestly, Matthew, we look forward to working with you again in the future. We're so happy you're a part of the whole Codesmith world. And yeah, thank you for being here. Have a great night.
Thanks.